Today we'll be using Gauss's law to solve another electric field problem where we calculate the electric field outside and inside of a sphere of charge, a dense sphere. Let's start by writing down Gauss's law in its integral form. Where we have the electric field dotted with the infinitesimal area vector, dA, is equal to the enclosed charge over epsilon naught, where the enclosed charge is the charge enclosed by some Gaussian surface of our choice. To set up the problem, let's draw a quick diagram where we have a sphere of charge. Let's say it has radius r. And we'll say that the charge density of this sphere is rho, and it's equal to the total charge on the sphere divided by the volume of the sphere, which will be 4 pi over 3 capital R cubed, where capital R is the radius of the sphere. Now we'll choose a Gaussian surface that fully encloses this sphere of charge in order to calculate the electric field outside of the sphere. Now we'll start with the electric field outside because it's easier. So looking at the left side of this equation, we have that the electric field is dotted with the infinitesimal area vector. Now, looking at this diagram, we notice that the electric field is radial in all directions coming off of the sphere of charge, and that the infinitesimal area vector is also going to be radial around this Gaussian surface as it was in some previous videos. So we find that inside this integral we have the dot product, which simplifies down to simply the magnitude of the electric field multiplied by the area, and that's because the two vectors are parallel at all points around this Gaussian surface. Moving forward, we can put this into the equation, and we have that the closed integral of the magnitude dotted with dA is equal to the enclosed charge over epsilon naught. And now because our Gaussian surface, we'll say our Gaussian surface has radius little r, because our Gaussian surface fully encloses the sphere of charge, we say that Q enclosed is simply Q total, the total charge on the sphere. The electric field will be constant in magnitude at all points around our Gaussian surface, so we can pull it outside the integral. And then the closed surface integral of our area element was simply going to be 4 pi r squared, where our r is the small r of the Gaussian sphere, and this is simply equal to Q total over epsilon naught. And we end up with that the electric field magnitude is equal to 1 over 4 pi epsilon naught Q total over little r squared. Now this is the same electric field as we found for the point charge and also for the hollow sphere in the region outside of the hollow sphere. And that's interesting since that if you're infinitesimally far away from this charge configuration, you can't actually distinguish between the three. Now let's calculate the electric field inside our sphere of charge. So I've already drawn the Gaussian surface here in red, where the Gaussian surface is inside the sphere and it has radius little r. Now obviously you can tell by this diagram here that the Gaussian surface isn't going to fully enclose all the charge encapsulated in this sphere here. So that will come into play in our Q enclosed on this side of the equation. On the left hand side of the equation, however, we're going to follow the same steps as we did for the electric field outside, and it ends up with being the same result, where the magnitude of the electric field times 4 pi r squared is equal to 1 over epsilon naught times Q enclosed. And this 4 pi r squared, the r squared, comes from the radius of our Gaussian surface inside the sphere of charge. The only thing different in this case as to electric field outside of the charge is this Q enclosed. So we worked through to find what Q enclosed is. We find that Q enclosed is equal to the integral of the charge density multiplied by the volume element dV. Now remember that we talked about that the charge density was constant over the entire surface of the sphere and throughout the sphere as is this dense sphere of charge. So we can pull it outside the integral. Rho is equal to the integral of dV, and we end up with the fact that this integral here is simply 4 pi over 3 r cubed, where here we use little r because it's the volume of our Gaussian surface with radius little r. So working through with this, we can also substitute in what we found for rho before. So this becomes the Q total, 4 pi over 3 little r cubed, 4 pi over 3 big R cubed, and the equal cancel. And we end up, if we substitute this back into this equation here, we have that the electric field is equal to 1 over 4 pi r squared epsilon naught. We substitute this in, q total, r cubed over r cubed. So this comes from our q enclosed, and this comes from the rest of the equation that we had up here. And by canceling this with this, we end up with that the electric field is equal to 1 over 4 pi epsilon naught, the magnitude of the total charge times the little radius of our Gaussian surface inside over the entire radius cubed. Now that we found the electric field outside and inside of the sphere of charge, let's find out what happens at the boundary. So for inside the sphere of charge, we have that the electric field is 1 over 4 pi epsilon naught, the total charge, little r, or r cubed. And we'll just talk about the magnitude for now, because we know it's radial. So at the surface of this sphere of charge, little r is going to equal capital R. So the magnitude becomes capital R over r cubed, because little r, our Gaussian sphere, will equal the radius of the outer sphere. And we find that this cancels, and we end up with that the magnitude of the electric field at the surface is 1 over 4 pi epsilon naught, this constant that's always present, times the total charge on the sphere, times 1 over r squared. And now this is important because if we look at the electric field outside of the sphere, we replace our little r squared with capital R squared, the radius of our sphere of charge. We find that the electric field magnitude is also 1 over 4 pi epsilon naught, q total 1 over capital R squared, and that these two are equal. And now this is important because of the continuity of the electric field as we move from inside the sphere of charge to the outside of the sphere of charge. And at the surface, the two electric fields should be the same.